In mathematics, the discrete Fourier transform converts a finite list of equally spaced samples of a function into the list of coefficients of a finite combination of complex sinusoids, ordered by their frequencies, that is those same sample values. It can be said to convert the sampled function from its original domain to the frequency domain. The input samples are complex numbers, and the output coefficients are complex as well. The frequencies of the output sinusoids are integer multiples of a fundamental frequency, whose corresponding period is the length of the sampling interval. The combination of sinusoids obtained through the DFT is therefore periodic with that same period. The DFT differs from the discrete-time Fourier transform in that its input and output sequences are both finite. It is therefore said to be the Fourier analysis of finite-domain discrete-time functions. The DFT is the most important discrete transform, used to perform Fourier analysis in many practical applications. In digital signal processing, the function is any quantity or signal that varies over time, such as the pressure of a sound wave, a radio signal, or daily temperature readings, sampled over a finite time interval. In image processing, the samples can be the values of pixels along a row or column of a raster image. The DFT is also used to efficiently solve partial differential equations, and to perform other operations such as convolutions or multiplying large integers. Since it deals with a finite amount of data, it can be implemented in computers by numerical algorithms or even dedicated hardware. These implementations usually employ efficient fast Fourier transform algorithms. So much so that the terms Fft and Dft are often used interchangeably. Prior to its current usage, the Fft initialism may have also been used for the ambiguous term finite Fourier transform. Definition: the sequence of n complex numbers is transformed into an n-periodic sequence of complex numbers. Each is a complex number that encodes both amplitude and phase of a sinusoidal component of function. The sinusoid's frequency is kn cycles per sample. Its amplitude and phase are, where tan2 is the two-argument form of the arctan function. Due to periodicity, the customary domain of k actually computed is 0, an1. That is always the case when the DFT is implemented via the fast Fourier transform algorithm. But other common domains are a, n2-1, aa and a, n1, 2, as when the left and right halves of an Fft output sequence are swapped. The transform is sometimes denoted by the symbol, as in OR. Ec1 can be interpreted or derived in various ways. For example, it completely describes the discrete-time Fourier transform of an n-periodic sequence, which comprises only discrete frequency components. It can also provide uniformly spaced samples of the continuous DTFT of a finite-length sequence. It is the cross-correlation of the input sequence, xn, and a complex sinusoid at frequency kn, thus it acts like a matched filter for that frequency. It is the discrete analogy of the formula for the coefficients of a Fourier series, which is also n-periodic. In the domain AA, this is the inverse transform of Ec1. The normalization factor multiplying the DFT and IDFT and the signs of the exponents are merely conventions, and differ in some treatments. The only requirements of these conventions are that the DFT and IDFT have opposite sign exponents and that the product of their normalization factors be 1 per Newton. A normalization of both the DFT and IDFT, for instance, makes the transforms unitary. In the following discussion the terms sequence and vector will be considered interchangeable. Properties: completeness. The discrete Fourier transform is an invertible, linear transformation, with denoting the set of complex numbers. In other words, for any NA0, an n-dimensional complex vector has a DFT and an IDFT which are in turn n-dimensional complex vectors. Orthogonality: the vectors form an orthogonal basis over the set of n-dimensional complex vectors. Where is the Kronecker delta? This orthogonality condition can be used to derive the formula for the IDFT from the definition of the DFT, and is equivalent to the unitarity property below. The Plancherel theorem and Parseval's theorem, if xk and ik are the DFTs of xn and n respectively, then the Plancherel theorem states, where the star denotes complex conjugation. Parseval's theorem is a special case of the Plancherel theorem and states. These theorems are also equivalent to the unitary condition below. Periodicity. The periodicity can be shown directly from the definition. Similarly, it can be shown that the IDFT formula leads to a periodic extension. Shift theorem, multiplying by a linear phase for some integer m corresponds to a circular shift of the output, is replaced by, where the subscript is interpreted modulo n. Similarly, a circular shift of the input corresponds to multiplying the output by a linear phase. Mathematically, if represents the vector x, then, if, then, and, circular convolution theorem and cross-correlation theorem. The convolution theorem for the discrete-time Fourier transform indicates that a convolution of two infinite sequences can be obtained as the inverse transform of the product of the individual transforms. An important simplification occurs when the sequences are of finite length, n. In terms of the DFT and inverse DFT, it can be written as follows, which is the convolution of the sequence with a sequence extended by periodic summation. Similarly, the cross-correlation of AA and AA is given by, when either sequence contains a string of zeros, of length L, and L plus one of the circular convolution outputs are equivalent to values of A. Methods have also been developed to use this property as part of an efficient process that constructs AA with an OR sequence potentially much longer than the practical transform size. Two such methods are called overlap save and overlap add. The efficiency results from the fact that a direct evaluation of either summation requires operations for an output sequence of length n. An indirect method, using transforms, can take advantage of the efficiency of the fast Fourier transform to achieve much better performance. Furthermore, convolutions can be used to efficiently compute DFTs via Radar's Fft algorithm and Bluestein's Fft algorithm. Convolution theorem duality. It can also be shown that, which is the circular convolution of and trigonometric interpolation polynomial, the trigonometric interpolation polynomial, for n even, for n odd, where the coefficients xk are given by the DFT of xn above, satisfies the interpolation property for even n. Notice that the Nyquist component is handled specially. This interpolation is not unique. Aliasing implies that one could add n to any of the complex sinusoid frequencies without changing the interpolation property, but giving different values in between the points. The choice above, however, is typical because it has two useful properties. First, it consists of sinusoids whose frequencies have the smallest possible magnitudes. The interpolation is band-limited. Second, if they are real numbers, then is real as well. In contrast, the most obvious trigonometric interpolation polynomial is the one in which the frequencies range from 0 to, similar to the inverse DFT formula. This interpolation does not minimize the slope, and is not generally real-valued for real. Its use is a common mistake. The unitary DFT. Another way of looking at the DFT is to note that in the above discussion, the DFT can be expressed as a van der Moen matrix, introduced by Sylvester in 1867. Where is a primitive nth root of unity. The inverse transform is then given by the inverse of the above matrix. With unitary normalization constants, the DFT becomes a unitary transformation, defined by a unitary matrix, where det A is the determinant function. The determinant is the product of the eigenvalues, which are always or as described below. In a real vector space, a unitary transformation can be thought of as simply a rigid rotation of the coordinate system, and all of the properties of a rigid rotation can be found in the unitary DFT. The orthogonality of the DFT is now expressed as an orthonormality condition. If X is defined as the unitary DFT of the vector X, then, and the Plancherel theorem is expressed as, if we view the DFT as just a coordinate transformation which simply specifies the components of a vector in a new coordinate system, then the above is just the statement that the dot product of two vectors is preserved under a unitary DFT transformation. For the special case, This implies that the length of a vector is preserved as well. This is just Parseval's theorem. A consequence of the circular convolution theorem is that the DFT matrix F diagonalizes any circulant matrix. Expressing the inverse DFT in terms of the DFT, a useful property of the DFT is that the inverse DFT can be easily expressed in terms of the DFT, via several well-known tricks. First, we can compute the inverse DFT by reversing the inputs. As usual, the subscripts are interpreted modulo n. Thus, we have. Second, one can also conjugate the inputs and outputs. Third, a variant of this conjugation trick, which is sometimes preferable because it requires no modification of the data values, involves swapping real and imaginary parts. Define swap as with its real and imaginary parts swap euro that is, if then swap is. Equivalently, swap equals. Then. That is, the inverse transform is the same as the forward transform with the real and imaginary parts swapped for both input and output, up to a normalization. The conjugation trick can also be used to define a new transform, closely related to the DFT, that is involatile euro that is, which is its own inverse. In particular, is clearly its own inverse. A closely related involuntary transformation /2 is, since the factors in cancel the two. For real inputs, the real part of is none other than the discrete Hartley transform, which is also involuntary. Eigenvalues and eigenvectors, the eigenvalues of the DFT matrix are simple and well known, whereas the eigenvectors are complicated, not unique, and are the subject of ongoing research. Consider the unitary form defined above for the DFT of length n, where this matrix satisfies the matrix polynomial equation. This can be seen from the inverse properties above. Operating twice gives the original data in reverse order, so operating 4 times gives back the original data and is thus the identity matrix. This means that the eigenvalues satisfy the equation. Therefore, the eigenvalues of the fourth roots of unity is +1, a 1, plus I, or ai. Since there are only 4 distinct eigenvalues for this matrix, they have some multiplicity. The multiplicity gives the number of linearly independent eigenvectors corresponding to each eigenvalue. The problem of their multiplicity was solved by McClellan and Parkes, although it was later shown to have been equivalent to a problem solved by Gauss. The multiplicity depends on the value of n modulo 4, and is given by the following table, otherwise stated, the characteristic polynomial of is. No simple analytical formula for general eigenvectors is known. Moreover, the eigenvectors are not unique because any linear combination of eigenvectors for the same eigenvalue is also an eigenvector for that eigenvalue. Various researchers have proposed different choices of eigenvectors, selected to satisfy useful properties like orthogonality and to have simple forms. A straightforward approach is to discretize an eigenfunction of the continuous Fourier transform, of which the most famous is the Gaussian function. Since periodic summation of the function means discretizing its frequency spectrum and discretization means periodic summation of the spectrum, the discretized and periodically summed Gaussian function yields an eigenvector of the discrete transform. A closed-form expression for the series is not known, but it converges rapidly. 2 other simple closed-form analytical eigenvectors for special DFT period n were found. For DFT period n equals 2l plus 1 equals 4k plus 1, where k is an integer, the following is an eigenvector of DFT. For DFT period n equals 2 liters equals 4k, where k is an integer, the following is an eigenvector of DFT. The choice of eigenvectors of the DFT matrix has become important in recent years in order to define a discrete analog of the fractional Fourier transform. The DFT matrix can be taken to fractional powers by exponentiating the eigenvalues. For the continuous Fourier transform, the natural orthogonal eigenfunctions are the Hermite functions, so various discrete analogues of these have been employed as the eigenvectors of the DFT, such as the Kravchuk polynomials. The best choice of eigenvectors to define a fractional discrete Fourier transform remains an open question, however. Uncertainty principle, if the random variable xk is constrained by then may be considered to represent a discrete probability mass function of n, with an associated probability mass function constructed from the transformed variable. For the case of continuous functions p, x, and q, k, the Heisenberg uncertainty principle states that where do, x, and do, x, are the variances of x2 and x2 respectively, with the equality attained in the case of a suitably normalized Gaussian distribution. Although the variances may be analogously defined for the DFT, an analogous uncertainty principle is not useful, because the uncertainty will not be shift invariant. Still, a meaningful uncertainty principle has been introduced by Massa and Spindle. However, the Hirschman entropic uncertainty will have a useful analog for the case of the DFT. The Hirschman uncertainty principle is expressed in terms of the Shannon entropy of the two probability functions. In the discrete case, the Shannon entropies are defined as and the entropic uncertainty principle becomes. The equality is obtained for Pn equal to translations and modulations of a suitably normalized Kronecker comb of period A where A is any exact integer divisor of n. The probability mass function Qm will then be proportional to a suitably translated Kronecker comb of period B equals Na. The real input DFT, if are real numbers, as they often are in practical applications, then the DFT obeys the symmetry, a where denotes complex conjugation. It follows that xo and xn/2 are real-valued, and the remainder of the DFT is completely specified by just n/2 minus 1 complex numbers. Generalized Dft, it is possible to shift the transform sampling in time and/or frequency domain by some real shifts A and B, respectively. This is sometimes known as a generalized Dft, also called the shifted Dft or offset Dft, and has analogous properties to the ordinary Dft. Most often, shifts are used. While the ordinary Dft corresponds to a periodic signal in both time and frequency domains, produces a signal that is anti-periodic in frequency domain and vice versa for. Thus, the specific case of is known as an odd-time odd-frequency discrete Fourier transform. Such shifted transforms are most often used for symmetric data, to represent different boundary symmetries, and for real symmetric data they correspond to different forms of the discrete cosine and sine transforms. Another interesting choice is, which is called the centered Dft. The centered Dft has the useful property that, when n is a multiple of 4, all 4 of its eigenvalues have equal multiplicities. The term GDFT is also used for the nonlinear phase extensions of Dft. Hence, GDFT method provides a generalization for constant amplitude orthogonal block transforms including linear and nonlinear phase types. GDFT is a framework to improve time and frequency domain properties of the traditional DFT, for example autocross correlations, by the addition of the properly designed phase shaping function to the original linear phase functions. The discrete Fourier transform can be viewed as a special case of the Z transform, evaluated on the unit circle in the complex plane. More general Z transforms correspond to complex shifts A and B above. Multidimensional DFT. The ordinary DFT transforms a one-dimensional sequence or array that is a function of exactly one discrete variable n. The multidimensional DFT of a multidimensional array that is a function of d discrete variables for n is defined by whereas above and the d output indices run from. This is more compactly expressed in vector notation, where we define n as d-dimensional vectors of indices from 0 to, which we define as where the division is defined as to be performed element-wise, and the sum denotes the set of nested summations above. The inverse of the multidimensional DFT is, analogous to the one-dimensional case, given by as the one-dimensional DFT expresses the input as a superposition of sinusoids, the multidimensional DFT expresses the input as a superposition of plane waves, or multidimensional sinusoids. The direction of oscillation in space is. The amplitudes are. This decomposition is of great importance for everything from digital image processing to solving partial differential equations. The solution is broken up into plane waves. The multidimensional DFT can be computed by the composition of a sequence of one-dimensional DFTs along each dimension. In the two-dimensional case, the independent DFTs of the rows are computed first to form a new array. Then the independent DFTs of Y along the columns are computed to form the final result. Alternatively, the columns can be computed first and then the rows. The order is immaterial because the nested summations above commute. An algorithm to compute a one-dimensional DFT is thus sufficient to efficiently compute a multidimensional DFT. This approach is known as the row-column algorithm. There are also intrinsically multidimensional Fft algorithms. The real input multidimensional DFT, for input data consisting of real numbers, the DFT outputs have a conjugate symmetry similar to the one-dimensional case above, where the star again denotes complex conjugation and the th subscript is again interpreted modulo. Applications: the DFT has seen wide usage across a large number of fields. We only sketch a few examples below. All applications of the DFT depend crucially on the availability of a fast algorithm to compute discrete Fourier transforms and their inverses, a fast Fourier transform. Spectral analysis: when the DFT is used for spectral analysis, the sequence usually represents a finite set of uniformly spaced time samples of some signal, where t represents time. The conversion from continuous time to samples changes the underlying Fourier transform of x, t, into a discrete-time Fourier transform, which generally entails a type of distortion called aliasing. Choice of an appropriate sample rate is the key to minimizing that distortion. Similarly, the conversion from a very long sequence to a manageable size entails a type of distortion called leakage, which is manifested as a loss of detail in the DTFT. Choice of an appropriate subsequence length is the primary key to minimizing that effect. When the available data is more than the amount needed to attain the desired frequency resolution, a standard technique is to perform multiple DFTs, for example to create a spectrogram. If the desired result is a power spectrum and noise or randomness is present in the data, averaging the magnitude components of the multiple DFTs is a useful procedure to reduce the variance of the spectrum. Two examples of such techniques are the Welch method and the Bartlett method. The general subject of estimating the power spectrum of a noisy signal is called spectral estimation. A final source of distortion is the DFT itself, because it is just a discrete sampling of the DTFT, which is a function of a continuous frequency domain. That can be mitigated by increasing the resolution of the DFT. That procedure is illustrated at sampling the DTFT. The procedure is sometimes referred to as zero padding, which is a particular implementation used in conjunction with the fast Fourier transform algorithm. The inefficiency of performing multiplications and additions with zero-valued samples is more than offset by the inherent efficiency of the FFT. As already noted, leakage imposes a limit on the inherent resolution of the DTFT. So there is a practical limit to the benefit that can be obtained from a fine-grained DFT. Filter bank, CFFT filter banks and sampling the DTFT. Data compression: the field of digital signal processing relies heavily on operations in the frequency domain. For example, several lossy image and sound compression methods employ the discrete Fourier transform. The signal is cut into short segments, each is transformed, and then the Fourier coefficients of high frequencies, which are assumed to be unnoticeable, are discarded. The decompressor computes the inverse transform based on this reduced number of Fourier coefficients. Some relatively recent compression algorithms, however, use wavelet transforms, which give a more uniform compromise between time and frequency domain than obtained by chopping data into segments and transforming each segment. In the case of JPEG 2000, this avoids the spurious image features that appear when images are highly compressed with the original JPEG. Partial differential equations: discrete Fourier transforms are often used to solve partial differential equations, where again the DFT is used as an approximation for the Fourier series. The advantage of this approach is that it expands the signal in complex exponentials inx, which are eigenfunctions of differentiation, ddx inx equals in inx. Thus, In the Fourier representation, differentiation is simply we just multiply by in. A linear differential equation with constant coefficients is transformed into an easily solvable algebraic equation. One then uses the inverse DFT to transform the result back into the ordinary spatial representation. Such an approach is called a spectral method. Polynomial multiplication. Suppose we wish to compute the polynomial product C, x, equals a, x, ab, x. The ordinary product expression for the coefficients of C involves a linear convolution, where indices do not wrap around. This can be rewritten as a cyclic convolution by taking the coefficient vectors for a, x, and b, x, with constant term first, then appending 0 so that the resultant coefficient vectors a and b have dimension a deg, a, x a plus a deg, b, x. Then, where C is the vector of coefficients for C, x, and the convolution operator is defined so. But convolution becomes multiplication under the DFT. Here the vector product is taken elementwise. Thus the coefficients of the product polynomial C, x, are just the terms 0. Deg, a, x plus deg, b, x of the coefficient vector. With a fast Fourier transform, the resulting algorithm takes arithmetic operations. Due to its simplicity and speed, the Coullier-Tukey Fft algorithm, which is limited to composite sizes, is often chosen for the transform operation. In this case, d should be chosen as the smallest integer greater than the sum of the input polynomial degrees that is factorizable into small prime factors. Multiplication of large integers. The fastest known algorithms for the multiplication of very large integers use the polynomial multiplication method outlined above. Integers can be treated as the value of a polynomial evaluated specifically at the number base, with the coefficients of the polynomial corresponding to the digits in that base. After polynomial multiplication, a relatively low complexity carry propagation step completes the multiplication. Convolution. When data is convolved with a function with wide support, such as for downsampling by a large sampling ratio, because of the convolution theorem and the Fft algorithm, it may be faster to transform it, multiply pointwise by the transform of the filter and then reverse transform it. Alternatively, a good filter is obtained by simply truncating the transformed data and retransforming the shortened data set. Some discrete Fourier transform pairs. Generalizations, representation theory. The DFT can be interpreted as the complex-valued representation theory of the finite cyclic group. In other words, a sequence of n complex numbers can be thought of as an element of n-dimensional complex space Cn or equivalently a function f from the finite cyclic group of order n to the complex numbers, Zn a C. So f is a class function on the finite cyclic group, and thus can be expressed as a linear combination of the irreducible characters of this group, which are the roots of unity. From this point of view, one may generalize the DFT to representation theory generally, or more narrowly to the representation theory of finite groups. More narrowly still, one may generalize the DFT by either changing the target, or the domain, as detailed in the sequel. Other fields. Many of the properties of the DFT only depend on the fact that it is a primitive root of unity, sometimes denoted OR. Such properties include the completeness, orthogonality, Plancherel-Pascal, periodicity, shift, convolution, and unitarity properties above, as well as many Fft algorithms. For this reason, the discrete Fourier transform can be defined by using roots of unity in fields other than the complex numbers, and such generalizations are commonly called number-theoretic transforms in the case of finite fields. For more information, see number-theoretic transform and discrete Fourier transform. Other finite groups. The standard DFT acts on a sequence x0, x1, x1 of complex numbers, which can be viewed as a function 0, 1, na1 a c. The multidimensional DFT acts on multidimensional sequences, which can be viewed as functions. This suggests a generalization to Fourier transforms on arbitrary finite groups, which act on functions g as C where G is a finite group. In this framework, the standard DFT is seen as the Fourier transform on a cyclic group, while the multidimensional DFT is a Fourier transform on a direct sum of cyclic groups. Alternatives. There are various alternatives to the DFT for various applications, prominent among which are wavelets. The analog of the DFT is the discrete wavelet transform. From the point of view of Tamiya frequency analysis, a key limitation of the Fourier transform is that it does not include location information, only frequency information, and thus has difficulty in representing transients. As wavelets have location as well as frequency, they are better able to represent location, at the expense of greater difficulty representing frequency. For details, see comparison of the discrete wavelet transform with the discrete Fourier transform. See also, companion matrix, DFT matrix, fast Fourier transform, FTPAC, FFTW, generalizations of Pauli matrices, list of Fourier-related transforms, multidimensional transform, notes. Citations. References, Brigham, E. Iran. The fast Fourier transform and its applications. Englewood Cliffs, New Jersey. Prentice Hall. ISBN A0-13-307505-2. Oppenheim, Alan 5. Schaefer, R.W. and Buck, J. A Discrete-time signal processing. Upper Saddle River, New Jersey. Prentice Hall. ISBN A0-13-754920-2. Smith, Stephen W. Chapter 8, The Discrete Fourier Transform. The Scientist and Engineer's Guide to Digital Signal Processing. San Diego, California. California Technical Publishing. ISBN A0-9660176-3-3. Corman, Thomas H. Charles E. Lesserson, Ronald L. Revest, and Clifford Stein. Chapter 30, Polynomials and the FFT. Introduction to Algorithms. MIT Press and McGraw-Hill PPA 822 848. ISBN A0-262-03293-7. ELISP Section 30.2. The DFT and FFT, PPA 830 838. P. DeHamel, B. Piron, and J. M. Ecchetto. On Computing the Inverse DFT. IEEE Trans. Acoust, Speech and Sig. Processing 36, 285 286 doi, 10.1109/29.1519 J. H. McClellan and T. W. Parks. Eigenvalues and eigenvectors of the discrete Fourier transformation. IEEE Trans. Audio Electroacoust 20, 66 €74 doi, 10.1109/TAU. 1972.11623442. Bradley W. Dickinson and Kenneth Steiglitz. Eigenvectors and functions of the discrete Fourier transform. IEEE Trans. Acoust, Speech and Sig. Processing 30, 25 €31 doi, 10.1109/TASSP. 1982.11638443. F.A. Gra 1/4 NBAUM. The eigenvectors of the discrete Fourier transform. J. Math. Anal. APPL 88, 355 €363 doi, 10.1016/0022-247 times opening round bracket 82 closing round bracket 90199-8. Nitik M. Atakishev and Kurt Bernardo Wolf. Fractional Fourier-Krug-Kook transform. J. Opt. Soc. Am. A14, 1467 €1477. Bibcode, 1997 JOSAA 14.1467A doi, 10.1364/JOSAA. 14.001467A, C. Candon, M. Akita and H. M. Ozaktas. The discrete fractional Fourier transform. IEEE Trans. On signal processing 48, 1329 Euro 1337. Bibcode, 2000 ITSP. 48.1329C DOI, 10.1109/78.8399880 Magdi Tawfiq Hanna, Nabila Philip At-Tawla Sif, and Walid Abd El-Magwid Ahmed. Hermite Gaussian-like eigenvectors of the discrete Fourier transform matrix based on the singular value decomposition of its orthogonal projection matrices. I.e. trans. Zik. Sist. I51, 2245 Euro 2254. DOI, 10.1109/TCSI. 2004.836850 Shamga Gurovic and Ronnie Hedani. On the diagonalization of the discrete Fourier transform. Applied and Computational Harmonic Analysis 27, 87 Euro 99. ARZIV, 0808.3281. DOI, 10.1016/JACA. 2008.11.003. Preprint editor, Shamga Gurovic, Ronnie Hedani, and Nesokhan. The finite harmonic oscillator and its applications to sequences, communication and radar. IEEE Transactions on Information Theory 54, 4239 Euro 4253. ARZIV, 0808.1495. DOI, 10.1109/TIT. 2008.926440. Preprint editor, Juan G. Vargas Rubio and Balu Santhanam. On the multi-angle centered discrete fractional Fourier transform. IEEE SIG. Proc. Let 12, 273 Euro 276. Bibcode, 2005 ISPL. 12273 VDOI, 10.1109/LSP. 2005.843762 J. Gooley, P. Lewis, and P. Welch. The finite Fourier transform. IEEE trans. Audio Electroacoustics 17, 77 Euro 85 DOI, 10.1109/TAU. 1969.11620360 FN Kong. Analytic expressions of two discrete Hermite Gaussian signals. IEEE trans. Circuits and Systems Euro 2, Express Briefs. 55, 56 Euro 60 DOI, 10.1109/TCSII. 2007.909865 External links, MATLAB tutorial on the discrete Fourier transformation, interactive flash tutorial on the DFT, mathematics of the discrete Fourier transform by Julius O. Smith III, fast implementation of the DFT, coded in C and under general public license, the DFT Euro OIP Euro mastering the Fourier transform in one day, explained, the discrete Fourier transform, wavetable Cooker GPL application with graphical interface written in C, and implementing DFT-IDFT to generate a wavetable set.